or up equals a 1, 0, and a down equals a 0, 1, again, in a z basis, all right? And so he represented this as a times 3i and 4.
Makes it normalized.
Okay? Okay, so we start there. The first question is to normalize this.
So it's psi star psi.
Okay.
But you gotta use, if you use the way you wrote it, you gotta use the bracket.
Okay.
Whereas the other way, you use a squared times 3i4 as a column, and then as a row, negative 3i4.
Good. So how about this? Just size, spin, general. Size, spin, right? This is the ket. This is the bra. So the ket in the matrix looks like this, the matrix representation. And the bra of that matrix representation looks like?
Negative 3i4.
That's right. So we can write it as, a times minus 3i4. And then over here, if you want, I'll just put an a squared over there. And it's going to be 3i4. And to normalize it, you set it equal to 1. 1.
Or you can say that the A and B are the amplitudes, like the up and down. Like and then 3i squared plus 4 squared has to be the 1.
You need an a there. You need the 3i.
The A too.
Look, 3i squared plus 4 squared is 25. That certainly doesn't equal 1. You need the normalization. Okay, with the a.
It'll be 3i A squared. And
Right.
3i A.
Okay, so you get a squared equals
1 over 25.
and a equals
It'll be 9.
1.
1 over 5. Yeah, 1 over 5. All right. And so what we find out is the following. This is one way to write it. Spin general equals 3i over 5 up plus 4 over 5 down. And again, I'm using a slightly different notation just so that you get used to it. All right? And again, I'm no longer to write. This is all on a z basis. Okay. The next question it asks is, what is the expectation? So find the expectation value of, I start off with z because it's the easiest, all right? So first of all, what does an expectation value mean? This is super important.
Where you're most likely to find.
Is it most likely?
The average.
It's the average.
For an
There's a
identity
difference.
variances.
All right? And what I encourage you to do is go right to the first chapter when he talks about likely, most likely, and average. Okay? But again, this is what this idea is that if you had an infinite number of identically prepared systems and you made this measurement on all of them, what would the average be? All right? And so when you calculate an expectation value, how do you do it?
You have to do the bra times with
Oh, with this.
You have to make the
Sandwich that in
bracket.
the middle between the two.
Yeah.
You sandwich it in the middle. You would know how to write it in an integral form if you had to?
Yeah.
Okay, good. And then it should go back to writing it in an integral form. It's kind of like getting psi star psi is kind of like the probability times the actual value, and that goes back all the way to the continuous probabilities, all the way back to the discrete probabilities.
This would be over dz for the integral?
This would be over, so there is no, it's over whatever space, right?
Yeah.
And there's no function here, and that's why it's kept out of that space. It stays in this abstract space, right? So I can't write over dz or anything. It's not a spatial.
Like I was just thinking how you would write the integral with a d something.
Yeah, you can't do this because it's not a spatial basis set, right? The basis set is spins. Right? Yeah, so we write this as psi general spin, and then the operator sz, and then again I'll put in a lot of extra notation.
psi star is the.
That's this. And then notice what I do is I put my little bracket under there to show this is in matrix form. All right, and so now it's going to be something like 1 over 25, I'll carry that out. It's going to be minus 3i, and then 4. Now,
So it's
what is the basis set we're working in? What is the problem
Z,
in?
so it's 1, 0, 0.
It's in a Z basis set, so I need the representation of the operator in the Z basis set. So it's going to be h bar over 2, 0, 0 minus h bar over 2. Don't forget h bar over 2.
Well, the book factors.
The polyspin matrix is 1 minus 1, but the spin matrix is h bar times the polyspin.
But it's a constant, so
The book actually factors H bar out.
Okay, yep.
you could factor in the
So
matrix.
then it's going to be 3i and then 4. And when you do it, what do you get? The answer for this one is, this is SZ, it's minus 70,
Minus 7 over
minus 7 over 50
H
H
bar.
bar. Okay? So again, what does that mean?
The execution that you'll find in the article.
So what am I measuring here?
I could take the time to spin Z.
I'm measuring the Z component of spin. And what I'm going to find out is that if I could do this hypothetically for an infinite number of things, the average value that I would get would be minus 7 over 50 H bar. Okay? All right, the next questions are to find the expectations of Sx and then Sy. And the only thing tricky here is that you just remember you're in a Z basis. And so you just want the representation for these operators in the Z basis. And again, those come from the polyspin matrices. All right, and so you can do them and crank them up. All right, now, this is the important thing. So my claim here, so here's my theory. This is my theory. My theory is this is my expectation value. Right? Okay, in real life, if I want to test this theory, I've got to do an experiment. Right? So if I go and do an experiment, can I really perform an infinite number of things? An infinite number of experiments? No. All right? So am I going to come up, if I go out and I do the experiment once, and I measure the projection in the Z, am I going to come up with that number?
Not necessarily.
You're not necessarily going to come up with it. So does that mean you're wrong? Does that mean your theory is wrong? No. All right? And so what it means is that I have to be able to compute not just the average value, but I have to be able to compute the theoretical amount of error that I could foreseeably see, the standard deviation. Okay? And that's the sigma, and that's the next part of the question. All right? So the next part of the question is to ask for the uncertainties, which are sigma. So this is the first part. Is the next is calculate the sigma, and we'll say sigma z.
Well, it says first you got to know what S squared is.
Okay, so what is this? So physically, what is it? Like whenever I draw in a lab, right, I give the answer as x plus or minus
error
something,
value.
right?
Mm-hmm.
And what is the plus or minus something?
Your sigma is your error.
Okay, and it's the standard deviation.
Which is your error.
Okay, which is my measure of precision, essentially.
It's like how far away from the
How far away from the average, all right? So what you should do is, if you don't remember, back in the earlier chapters, and you should check this, there's a proof that shows where this sigma comes from. And this sigma comes from the definition of the standard deviation. All right? And sigma actually equals, so it equals the standard deviation. Okay, so that puts us on a footing that we're familiar with. And that standard deviation can be expressed as the expectation value of SZ squared minus
SZ quantity squared.
quantity squared. Okay, so this is significant, everybody. All right, because this brings us back down to the real world, all right, where we can't do an infinite amount of measurements. We really need to know, we need to test, does our theory equal the experiment? All right, and if our theory just said this and our experiment didn't equal that, there'd be a great deal of problems. All right, so our theory also tells us that based on this, that we will have a standard deviation of precision. And so we have to compute this. All right, and the way we compute this is, and I'll just sketch this out, is how you compute this guy.
Which one? The first one?
Yeah.
You square them individually and add them up, and then add them all.
How would you
do,
write it?
you write it in between with the S
Okay.
squared.
So you write it psi g spin and sg squared psi g spin minus psi g spin sz psi g spin quantity squared. Okay, we know what the operator is for sz. Right? We know what that operator is, it's just this thing. It's the Pauli spin matrix. So how do I compute S squared z?
You square
Multiply.
SZ. and
Matrix multiply.
It's just sz times sz, which equals h bar over 2, 0, 0, minus h bar over 2, all times h bar over 2, 0, 0, minus h bar over 2.
H bar squared over 4.
Okay. All right, and so you put all that stuff in there, and you have to be able to do it, and it takes a lot of pages, and it takes a lot of time. It's not hard, but it takes time. And then when you do this for SZ, the answer is
12 over 25 H bar.
I gotta put my solutions.
No, I got a question first.
Yep, go ahead.
He said in the solution that it will always be h bar squared over 4 for the square of the x, y, and z components of spin. How would you have known that it would always be h bar? I mean, like, you get h bar squared over 4 for all of them, but
Okay, I'm sorry.
he said that for all the components, when you square the x, y, and z component, you always get h bar over 4, h bar squared over 4. How would you have known that you all? Is that something that's proved somewhere, or?
No, so I think it will be is this, is if the eigenvalue for SZ,
Yeah.
an eigenvalue is h bar over 2 plus or minus h bar over 2, then the eigenvalues for s squared are always going to be those things squared. All right, so just knowing that the eigenvalues in that basis are h bar plus or minus h bar over 2, squaring that.
Squaring it, you get
h squared over squared over 4.
Mhm.
Okay. All right, and what we come up with this is sigma sz equals, and again, I posted the solutions. Did everybody see the solutions? So the solutions I've been putting up, all right? So work with them as you need them, but again, you must bang your head first. Bang your head trying before you go right to the solutions. But this comes up to be, let's see, sigma sz equals, what is it, 12/25ths? 12/25ths h bar. All right, so here, as a theorist, that you're going to, pose your theory to the experimentalists that are going to do it, is your final answer is that SZ, your expectation is going to be minus 7/50ths h bar, plus or minus, maybe I'd write it as 24/50ths h bar. All right, so that's a big range, right? Plus or minus 24, all right? And so how can you really make this experiment tighter, make your theory better? So that's the standard deviation.
Do 2 standard.
Okay, you can do 2 standard deviations, but really, if this is a standard deviation, all right, what this answer really is not quite right. Right, so remember, a standard deviation is the precision. If I do an experiment once, what do I say the error is? The standard deviation. But what if I do an experiment a whole bunch of times?
Standard deviation divided by the square
Square
root
root of n. So over here, I really want to divide by the square root of n. That's what I would want to pose to my experimentalists. And so if I do this experiment 100 times, so if you take 100 measurements, then what you're saying to the experimentalist is, look, you better get an answer, 7/50 plus or minus, what would that be, like 2.4/50 times h bar. Okay? You know, I'm so tempted, like, I don't even look to take these things and just drink it, you know?
Oh, it's just water and, food coloring.
Yeah.
Well, it's probably,
It's from thermal physics last week.
that's probably science building water, though, so.
All right, so this is a good problem, all right, because it's a nice connection to something that we actually calculate, all right? All right, so the next problem I asked you guys to do was what? A couple, you know, like 429 is a good problem. I think I posted the solutions for 429 or something like that. That's a nice problem. And 429, it asks for the eigenvalues and the eigenspinors of Sy. Okay, so the eigenspinors of Sy means what? What am I looking for?
Same, things, eigenvalues, eigenfunctions.
I'm looking for the eigenfunctions, all right? But, you know, terminology matters, so they're not really functions, so they're eigenkets of Sy in a what basis? In the Z basis. I didn't ask you to turn that one in there, okay? All right, so that was 429. All right. The next thing that I asked you to do is to go over the problem on Lamore precession. All right? And so going over the problem on Lamore precession,
You have to start with the picture.
I didn't mention this the other day, and Dale brought it up to me that he finally figured it out. I know I mentioned it in the last semester, but let me set up the problem anyway. All right, for the Lamore precession. All right, in the Lamore precession, the idea is a spin half particle. So Lamore, let me get the spelling right, it's O-R, Lamore precession. Okay, it's a spin half particle at rest. Right? And so the hardest thing in physics, I always say, is how do you start a problem? All right? Honestly, it is the hardest thing. All right? And if you're dealing with classical stuff, it's draw a picture and write down F equals ma. All right? That's a good place to start. And if it's a quantum mechanical problem, draw a picture and start with Schrödinger's equation. So in a constant B field. B0 Z hat. All right, so this problem kind of looks like this. Here's B0 Z hat, and then here's my spin half particle. So there's a spin hat. And then I'm going to represent my spin half by a mu, a magnetic dipole. All right, so Schrödinger's equation is H times psi, maybe it's going to be a ket, maybe I'll make a capital psi because it's going to be the time-dependent Schrödinger equation, equals IH partial with respect to t of psi. Okay, so the very first thing that we need to do is figure out what? Figure out the Hamiltonian. All right, and so the Hamiltonian, what we know is the Hamiltonian, generally speaking, equals H0. So H0, I'm going to call my EK plus EP, my kinetic plus my potential, and the minus h bar squared over 2m second derivative plus the potential. That's my unperturbed Hamiltonian. All right, and now I'm going to add, for this new problem, I have a magnetic dipole and a magnetic field. Now the Hamiltonian is the total energy. So is there a new energy that I need to add in addition to the H0? I need to add the energy of a magnetic dipole and a magnetic field. All right? And the energy of a magnetic dipole, we went over this last time, right? Remember when we drew out everything? Okay, it's important to know that curve. You know, like it turns out that H mu dot B, I don't know, you could write it out explicitly, and I will write it out explicitly in a second. But for our particular problem, what is H0, the unperturbed Hamiltonian?
Zero.
It's zero,
At rest.
because it's at rest and there's no electrical potential, right? No gravitational potential. So this is zero, all right? And so let's write this out explicitly. So H, if you want, put in a subscript total, H total. So H total equals minus mu dot B. All right? Mu, we learned last time. So here's the general form. Here's what we learned last time, and I expect all of you guys can know this at any time. Mu L, for general angular momentum, equals G cubed over 2mL. That's the thing we derived last time for a specific case. And here we have mu s, right? Let me put an s there for a spin. Here we have mu spin. So what does mu spin equal to?
GQ over 2M.
Yeah. Over 2me and then s, that's right. The only thing that changes it has to do with s. So Griffiths calls this equal to alpha s, the vector. So if we go back up here to the total Hamiltonian, it equals minus alpha s dot b0 z hat. That's a dot product between the s and z hat. And what's the dot product between the s and the z hat? That equals sz. So this equals minus alpha b0 sz.
It's gamma.
Is that?
It's a gamma.
Oh, gamma. Why am I saying alpha? Thank you.
Because you're looking outside.
Yeah, everybody tilt their head.
If you lie down for a second.
Look, they're just different representations of the same thing under some type of Lie group of rotation, all right? So good.
Let's find the transform.
Find the transformation that makes what I... So your goal is always find the transformation that makes what I say correct.
Right.
And the representation to whatever I say is right.
Right.
Okay. So look, we've got this. So we're on our way. We have what the Hamiltonian is. And the big kicker in this problem is, so here's what you would do. Once you've got the Hamiltonian, then what you then do is you go into Schrodinger's equation.
Plug in SZ as a matrix.
Yeah, but let's think this through a little bit more, okay? So you plug this in, okay? And then what do? You separate out time. So here's what you do. You would start off with this. Once you have the Hamiltonian, you'd separate out time and just say g of t equals e to the minus I e over h bar times time, right?
That was T over H bar.
Yeah, h bar, right? And then you would be left with h times little psi cap equals en times psi n cap. Put an n and anticipate many solutions. All right, and then what I'd do is then I'd put in the Hamiltonian, I'd work hard to find the psi n's. All right, and what would these psi n's be?
Spin down.
Those would be my basis set.
Up and down.
They would be my stationary basis sets. All right? All right, then once I found my stationary basis set, so here are the steps, and again, this goes right back to what we did last semester. All right, once I've got that, then what would I do is I would make a psi general
Which would
equal,
some constant times.
okay, so some constant Cn times e to the minus I en over h bar t times psi n, where I'd sum over the basis.
If this
Sum over n to
be
Cn.
psi n at t equals 0.
And then I could solve for the c, oh, I need a Cn right here. Sum over n of Cn right? So what I've done is I've got a complete basis set, it's a stationary basis set, and now I'm finding the projections onto the basis set. So then the next step would be to find the CNs. And the way you get the CNs is you go something like this. Oh, guys, let's be careful with my notation. Let me go back to a capital psi. Why do I want to go back to a capital psi?
Because you're
Time
not going to
dependent.
lose time.
I put the time dependence back in, okay? And then to find the CNs, I would go psi of t equals 0, and then look at the overlap with psi general. All right, and I'd be able to find my CNs. Okay, but here's the step where you kind of have to do the work. This is the step where you have to do the work. Right? This is where we did the work before solving the DiffDq. We had to do that. Okay. Here's
Plug
what.
the Hamiltonian in, which is the negative gamma B0 SZ.
Yep,
You can solve for what E would be.
that's right. But check this out. You're 100% right. But here's another way you can do this, right? All right. Let's look at the commutation. Of SZ and H total. Okay? Why? Okay. And the answer is, I know what the eigenbasis is, or the eigenkets, or the eigenspinors of SZ are. They're up and down, right? Okay, so if this equals 0, if it's true that that equals 0, then what does that tell me?
Then they share.
They share the eigenfunctions. Do I already know the eigenfunctions or the eigenspinors?
Yes.
Yeah, so I don't have to do any work. That's the big kicker. All right? So the big kicker with this problem, and Griffiths goes through and kind of does it all nonchalantly. So I'm kind of doing it very explicitly here. All right, so let's check. So what we have is SZ, and then the total Hamiltonian that we found out is minus gamma B0 SZ. All right, and you can pull out these constants, so it's minus, well, the constants don't matter. So in the multiplication of ordinary numbers, the commutation, they satisfy the commutation relationship where that doesn't matter. All right, so this is simply SZ and SZ, the commutation of SZ and SZ. And does that order matter if it's SZ and SZ?
No?
That order doesn't matter, so does this mute?
Yes.
Yes. So what we get is, therefore, the up and down eigenspinors equal the eigenspinors of SZ and of our H total. All right. And so the rest of the problem proceeds in the normal way. Is now you know what the eigenspinors are. They're up and down, a 1 and a 0. All right, and you can plug those in. And you can plug those into this equation right here. So you plug in, so now you have two eigenspinors. So you would plug in, for example, so now use our solution over here. We would use minus gamma gamma B0 SZ H bar over 2 times 1, 0, 0 minus 1 times, for example, in up would be a 1, 0. That has to equal